Hello, this is chapter 17 of the Top Hat Organic Chemistry textbook, the second edition. In this one we're going to be talking about conjugated systems, the Diels-Alder reaction, as well as UV-Vis spectroscopy. So for conjugated systems, what we mean is that you have carbon-carbon double bonds, essentially, where they're oriented in a double single orientation. Okay? Stuff like that. So when that happens, we call it conjugated. The reason why this is important is because what ends up happening is all of the p orbitals on the carbons, they're all sp2, so they're going to have this unhybridized p orbital. All of these are going to be in alignment here, and so these pi electrons can go and move between all of these carbons. You can have what are called accumulated dienes, and for that one you do have two p orbitals. However, their p orbitals are in the wrong orientation. Okay, so one is up like this, one is like this. Okay, because this central carbon is sp hybridized, the other set of p orbitals that are unhybridized are going to be sitting 90 degrees from the other. Okay, so these electrons here can't interact with these ones over here. Okay. With isolated dienes, they could get in alignment. However, these p orbitals could get in alignment. However, there's a break in between. Okay, and so there's a gap between where these pi orbitals or p orbitals are here and over here, and so they can't bridge that divide. Okay, and you can have these oriented for the unsaturated hydrocarbons. You can have all sorts of orientations with them. They can be at the ends, they can be in rings, they can be in the cis and trans configuration. That doesn't matter. But if you're looking at conjugated systems, they have to go in this double single. Now they don't have to go all the way to the end, right? So if you're here, this is a conjugated system because double single, but nothing over here. As long as at least you've got two bonds, two double bonds, and they go double single, you've got a conjugated system. This is not conjugated, so even though it's got two double bonds, you have these breaks in between. But here you got double single. Okay, same thing here, double single. Okay, so that's how you recognize a conjugated system. Okay. Now, one of the things about carbon-carbon bonds is if you have a sp2 associated with a carbon associated with that bond, it's going to shrink. Okay, and so if you with sp3s, right, you're going to have say 1.54 angstroms here. But if you have two sps, right, they're part of a double bond, right? Remember, those things shrank. Okay? But it doesn't matter if both of these are sp2, or even just one of these is an sp2. Okay, so even here they're both sp2, but even this single bond in here is shorter than a normal sigma bond. Okay, so so having an sp2 carbon as associated with the bond is going to shorten that bond length. Now, one of the things with stability is, so for here, this is actually reacting with you're removing H2, but we can also look at this as far as like burning the reaction. What's going to happen is, as things become less stable, right, they give off less energy. Okay, that's the reason why you make bombs out of things that are unstable, because they will give a larger punch. Okay, stuff like that. So it turns out that when you compare, just say a couple of these alkenes, right? So by that, so if you just have the one alkene in here, compared to the conjugated system, this actually has a much higher energy associated with it. And what that means is that the double bond, this conjugation, okay, provides some stability. And the reason for that is because you can get resonance forms. Okay, so these here, this is the major form for that for the system, but you can actually go through each one of these. These are all valid resonance forms, and typically the more resonance forms that you can get, the more stable the system, the overall system, is going to be. Okay. Now there is a couple of different ways that these can be oriented. Okay, so you can have what's called the S-cis and S-trans. Okay, so remember, you can get free rotation around this bond. The problem is, when it's oriented like this, you can have the steric clashing between these two hydrogens, right? So these guys are starting to invade each other's personal space, the electron clouds, and so this is quite unstable. Okay, and this is what's called the S-cis form. What it really wants to do is it really wants to rotate around here to get these two hydrogens as far apart as possible. Okay, so all these hydrogens have their own personal space to relax in. Okay, so it's going to, so getting it into this orientation is going to cost you some energy because you're trying to put these two hydrogens directly next to each other. Now, one of the things, okay, so getting back to the carbons, right? So is that when you are working with these, okay, and when you're working with these conjugated systems, having a charge immediately adjacent to next to a double bond makes this charge incredibly stable, the system incredibly stable, right? Because we can do a resonance structure where we move this over here, and so we can give this as fourth bond, but that results in this carbon number 1 having having its electron, having a positive charge. However, so it means is that part of the time carbon 3 is going to have that charge, part of the time carbon 1 is going to have a charge, and so since neither one of those carbons is always going to have the charge, it's much easier for them to be able to handle this, right? And so what the actual structure for this is these systems sliding around, going between these two carbons, right? So there's effectively a 1.5 bond between these two, 1 and 2 and 2 and 3, and each carbon 1 and carbon 3 only has essentially a half a bond, or half a positive charge, because half the time the charge is over here, half the time the charge is over here, and so that provides quite a bit of stability. And so if you look at the order of how stable these things are, having the positive charge immediately adjacent to a double bond provides incredible stability. So here you have a primary carbocation that's really unstable. However, if you're next to a double bond, right, you can get that resonance stabilization. So now it's equivalent to, say, a secondary. Okay. One thing to note is that if you put that charge directly on a carbon-carbon bond, that's incredibly unstable, because again the orbitals are misaligned, and so we can't get the stabilization. Only when it's next door can we, so we can get those orientation, the p orbitals aligned. Otherwise, for here, the orbitals that associated with the pi bond are, say, like this, the orbital that has the positive charge is like this, and so it's 90 degrees from each other, and so they can't help each other out. So these are really, really unstable. Now, one of the things that you can do with this is you can, if you just have, say, if you just had a regular old alkene, right, you're going to get that product, no big deal. The problem is, if you add this in conjugation, what's going to happen is you can also get some what are called 1,4 additions. So if this is carbon 1, 2, 3, 4, right, we're going to get 1,2 addition, where we get the hydrogen on the 1 and the chlorine on the 2, or you can get what's called 1,4 addition. So 1, 2, 3, 4. Hydrogen goes on 1, chlorine goes on the 4. Okay, and so you're going to get a mixture of the two, and it all has to do with the fact that there's resonance that can happen. Okay, so after you do the first step, right, so you've got negative charge here, you've got partial positive, partial negative, right, so this has a lot of negative character to it because it's got all those electrons, and so that's going to get attracted to this hydrogen. We're going to make a bond here, and we're going to push these electrons onto the chloride. Okay, and so you've got what you can do is, so if we put the hydrogen here, right? Markovnikov says that's what we need to do. Okay? But that, right, because this is primary, right? That's secondary, right? So we want to put the hydrogen here so the chlorine can come here. What can happen is while we're waiting for the chloride to come in and attack, what's going to happen is you're going to get this resonance structure where you're going to come in here and this is going to slide over there to create this. And so when the chloride comes in, it's going to see both forms of this. And so if it attacks, say this attacks here, you're going to make that product there. If instead it sees this version, this resonance structure, it's going to attack here, and that's going to form that product there. And so wherever that positive charge is, that's where the chlorine is going to attack. Okay, so that's how you get the mixture of the 1,2, which is right here, and 1,4. And so it's just a little quirk on adding onto the a normal alkene reaction. Okay, now when you're going on here, okay, you want to make sure that this positive charge is immediately next to the double bond, because otherwise you're not going to be able to take advantage of the resonance stabilization. Right? This pi bond here is too far away because you've got a break here. Right? There's no right? This guy can't help out, and so they're too far away. So when you're adding the H, what you want to do is when you add the H, you want to make sure that that positive charge is right next to the alkene. Okay, this becomes so and so you can also do this with BR. Okay, so you get BR, so you can do all sorts of crazy resonance, and actually this should be 1/6 addition, but that, so you can get here, but it's no different than if you had an HBr. You have an H over here and a BR over here, but these things can get kind of crazy. Now, how does this work? Okay, so for here, we're going to add water. However, this is no different than if we had, say, HCl. Okay, so if we were going to come in here and attack here, we've got two choices, right? We can add the hydrogen here, right? So this is where the original carbons were, here and here. We can add the carbon here and put the charge there, or we can put the, right, so carbon. We could put the hydrogen here, which results in the charge going on the other side. We don't want to come this route, right? Because this charge here is too far away from this double bond. So we don't want to do that reaction. We want to have it go here. And so in this case, the water is going to attack either there or it's going to go here, right? Because we're going to do that right? So we're going to do a resonance structure where we can slide that over, and so the positive charge is there, which results in an alcohol. Okay. If this was a HCl that we're adding, we would have chlorines attack either here or here. Now we can also do it with these carbons, right? So these carbons here, right? So it ends up being there and there, there and there, there and there, right? So for here we can either add we can add the hydrogen on this side of the double bond, or we can add it on this side of the double bond. If we add it, right, this looks really good because we put the tertiary carbocation here, so that's good. However, if we put the hydrogen here, we're not going to be adjacent to the double bond, so we're not going to want to go this way. We're going to want to go here so that we can do this. We can do the resonance structure. And so again, when the water comes in and attacks in this reaction, it's going to attack either here or there, because these are the two forms. So wherever that positive charge is, that's where we're going to have the water attack. And so what you end up getting is you end up getting four products. So here, here, and here, as well as the other places. All right, so you're going to get alcohol here, alcohol here, alcohol here, alcohol here, and but remember that where the double bond is positioned slightly differently with each one of those, so you have to take that into account. Okay. So the water would attack here, make this, and then another water would come grab this to make the OH. So you would either attack there or there. And then you would also do the ones from A. Okay. Next up are what are called the pericyclic reactions. So that's the sort of overall system where you have pi bonds are used to make new sigma bonds inside of these cyclic structures. There are cycloadditions, sigmatropic and electrocyclic. The book actually goes into sigmatropic and electrocyclic, but we're only going to deal with this what are called cycloadditions. Okay, and so we're going to make these cyclohexenes here. These things are really are a lot of fun, and they are actually quite useful synthetically, okay, for moving double bonds around, stuff like that. However, we just don't have time to work on it, so we're just going to talk about the cycloadditions. Okay, and in particular, we're going to talk about what's called the Diels-Alder reaction. Okay, so this was actually developed by two different labs, the Diels lab and the Alder lab, sort of roughly simultaneously. Okay, and it's used to make cyclohexenes. Okay, it's what's called a 4+2 cycloaddition, right? So here's the 4-carbon piece and then a 2-carbon piece. So that's what that means: a 4 and a 2 coming together to make a 6-carbon alkene, cycloalkene. But what's going to happen is, what we're going to do is we're going to take this bond here, and we're going to make it here. So we're going to make this bond is going to form here. Okay. This pi bond is going to make, so this pi bond here is going to make this. Okay. And since this guy can't have 5 bonds, we've got to, we're going to slide this guy here up to here to make an alkene. Okay, and so here's what it looks like, and so this is why so it's all of these electrons are kind of delocalizing, and so if you notice this transition state looks vaguely like a benzene. Okay, that's one of the big reasons why it works. Okay, and this is what's called a concerted reaction. All 3 of these arrows happen simultaneously. Okay, it's not this one and then this one and then this one. It's everybody going at the same time. Okay. And so if we look at this, right, so we can come in here, and so we've got these 4 carbons here, and then this diene, this is what's called a diene. Okay, and then we're going to have we're just going to be doing it on the carbon-carbon double bond here, the carbon-carbon double bond. We'll talk about the C double bond O, how that helps out. But what we're going to be doing is this is going to connect here, this is going to connect here, and this is going to slide here. And so what's going to end up happening is you're going to get this here. And so what we're going to get is this bond here, that bond there. And so we can fill in our hydrogens. Like that. So the one that people often miss is this guy here. We can't have, this carbon can't have 5 bonds, right? Oh, I'm sorry, this is a CH2. Because it's a CH2, right? And so it's got to shift these onto here. Okay? Not so bad, right? Yeah, it's flipped, but not a big deal. Now, one of the things is this: it has to be, the diene here has to be in this S-cis conformation. Now, I just said it doesn't like to be in that. Well, yeah, that's true, but it can't help otherwise. If it's in its preferred S-trans, this carbon here is going to be too far away from here to make the bond. Okay, and you won't be able to make this cyclohexene structure. Okay, and so it needs to get into the cis configuration. And so if it's locked like this reaction will never go. Okay, there's no way that this thing can orient so that it's in the cis configuration. Same thing with something like this. Okay, because if you try to rotate around this bond, which is legal, it's going to be really, really, really difficult to get these two methyl groups. You know, it's hard enough with with two hydrogens. With two methyls, it's going to be really terrible. It's going to be a tiny, tiny, tiny fraction of it. So this will be marginally faster than this one, only because this is a 0.0000, never going to work. Okay, stuff like that. So this is rarely, if ever, going to happen. Okay, because it can never get into this proper orientation, this S-cis configuration. On the other side, if you are locked into an S-cis configuration, so you have something like this, then it goes really rapidly. Okay, and so here's the diene here. Right, that's these guys here. Okay, and what ends up happening is this CH2 here kind of has to get out of the way. We're not breaking these bonds, so it just has to get out of the way. And so it's this right here. It's this one here. It's called a bridgehead because it looks like a bridge going from here to here. Something like that. And so, right, so carbon, 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 carbon. So we can get this sort of crazy cyclic structure. So here I like kind of drawing it like this because I think it's easier for students to see, but this is how it's often portrayed, how it's written. Lots of times what you'll see is a break between this carbon and this in that line. All that's saying is that this bond here is in front. Okay, so sometimes you'll see it written like this. What that means is this bond here is in front of this bond here. Okay? And so that's what that means. Okay? But it's actually really difficult to just buy this. You actually have to buy it already reacted and then have the reaction go backwards. It's kind of crazy. You can also have it again like this if you have the 6 carbon version of this, and again this is this CH2 here is this one here. We just got to get it out of the way. And so here it's a 2 carbon bridgehead. Like that. Now notice how this we want the acetylene, so we started with the triple bond. We only need to remove one of these to make the new bond. This one here, the other pi bond here remains. We just haven't reacted with it, so it's just going to stay put. Okay, so if you're reacting with a triple bond with an alkyne, you're only going to burn one of these pi bonds. The other one remains, okay, to leave the double bond behind. Okay. Now, if you look at this, so this is the diene, okay, and this is what's called the dienophile. That's this part here. This is the one that loves the dienes, okay? And so what we want on the dienes is what are called electron donating groups. And so these are things that can put electrons into the system, right? Putting a lot of, what we want to do is we want to make this as big as possible. Okay? Here in the dienophile, we want to put things that are electron withdrawing, right? We want to put positive charges next to here, so we can make this as, we can have this as positive as possible. Okay, so if we're sucking electron density away from these by having electronegative groups, okay, then this makes this much more attracted to the negative over here, positive here, so that they can come together. Now, the way that these things come together is because it's a concerted reaction. What ends up happening is these groups here, so these guys on one side are going to go together, okay? And so for here, they're going to go like this. the hydrogens that are on the other side, they are also going to go together. So they're going to be on the dash, like this. Okay. So for these guys, so if you have the trans, again, what we're going to get is we're going to get the C double bond O and this hydrogen going the same way. While this hydrogen and that C double bond are going to be on the wedge, or excuse me, on the dash. Okay, so these guys are going to go together. So left versus right on the diene tells you where you're going to want to go, and so as long as they go together, you're fine. Okay, so this is going to be you're going to have a mixture of, you could have also written this like this. Okay, and it's actually the same product. Just flipped. Right? In this case, it doesn't matter. Okay, it's just this just flipped. But for here, you're going to get the enantiomers, where one side is wedges, one side is dashes. Okay, one side is wedges. I usually have the right side be wedges and the left side be dashes, but you can do whatever you want. So if we're looking at this one, we're saying, what do we need to have in order to be able to make this product? Okay. So here is our diene. Right, so here's the diene. So we're going to need this. We're going to need to have it go like this. But for here, this is the dienephile. And so if we can't see it, it must mean it's a hydrogen. And so we need a wedge and a dash for both of them. If we know we're on the wedges, then we assume that the hydrogens are on a dash. And so what that means is the dienephile, both the C double bond O and the methyl group are going to be going on the same side. Like that. For here, again, the diene is right here. So again, that's going to look like this. But for here, the dienephile, now this one is a wedge and this one is a dash, and so that means this one over here, the dash is a hydrogen. Here, or the wedge is a hydrogen. Here, a dash is a hydrogen. So what's going to happen is these two hydrogens here, or these two groups that are on the wedge, are going to be on one side. Right, and then these two are going to be on the other side. Oops. Like this. Okay. And so these are the two bits that would produce this product. These are the two bits that would produce this Diels-Alder product. Okay. Now for some of these, so there is some stereochemistry that happens with the diene. So if these groups are hanging, sort of away from each other, they'll be either both wedges or both dashes. If one's pointed, if this is a trans and this is a cis right here, that means they're going to be, one's going to be a wedge and one's going to be a dash. Okay. Now again, for here, right, we're going to get this to here to here. What's going to happen is this bond here and this bond here, so these two bonds here have to go in the same direction. Okay, so you can't have like a wedge here and a dash here. Okay, they both have to go, because we got to slide this CH2 out of the way. And usually I have it go on a wedge, just out of tradition. Stuff like that. It's just, I got in the habit of it, so that's usually what I do. So that's kind of what I think. It's kind of pucked up, it's kind of puckered up like that, so that it can do the Diels-Alder reaction. Okay. Now, the way this works is, again, all of these are going to, this is a concerted reaction. all of these bonds are formed simultaneously, and it has to come in that these p orbitals have to, these things have to come in like this. The reason why that's important is that these p orbitals here are going to want to feel these p orbitals here. Okay, so the way that they come in is going to make a difference. Okay, and so if the groups that are on here, okay, with the p orbitals are faced in the same direction as the bridgehead here, okay, so this product would look like this, and then you would have the CO2 CH3. So since they're on the same side, right, that means they'll either both be up or both be down. Okay, because they're both on the right side. Okay, this is what's called the exoproduct, where they're both where these guys are facing the same directions here. So we're concerned about the things that have a pi bond on the dienophile. The endo product again, I usually draw the bridgehead going up, but for here, again, they have to go the same way because they're on the same side. And so for this one, they're going to be going this is if this is on the wedge, then these guys have to be on the dash. And so this is what's called the endo product, and this is the one that's almost exclusively formed. Okay? Because we need those p electrons to get underneath. We want to have the C double bond O's here, right? These C double bond O's here to interact with the p orbitals here. So as this moves up, that means these guys here go down. Okay, so if this bridgehead's going up, then these guys have to go down. So the exo approach would have it so that these aren't underneath, and so they would end up, it's these hydrogens that would be going in the opposite direction, and this is not what's formed. We want these p orbitals to be interacting with these p orbitals here. It's what's called pi-pi stacking. Okay? And so if you're looking at this one, so if we do a classic predict the product, okay? Here we just have a regular diene. We don't have the that diene with a ring. So this one is just a classic sort of, this attacks here, this attacks here, this goes here. So what we're going to get is here. Now, for this one, what we're going to get is these two guys are going to go one way. So let's say that's a wedge, Cn, hydrogen. And then these guys are going to go point in the opposite direction. So hydrogen, methyl. It doesn't matter, so even though this has p orbitals in it, it doesn't matter because there's no bridgehead. It only matters when there is a bridgehead we have to worry about. But the big thing is these two guys are going to be on a wedge, and these two guys are be on the dash. So they're going the same way. These two guys going one way, these two guys going the opposite way. If you have the bridgehead here, then it becomes a lot more complicated, because what's going to happen is you're going to need to find, so here's the dienophile. Okay, here's where that p orbital is. So if this is going to go up, then this has to go down, which means this whole side has to go down, which means this side has to go up. Or you can say, you can also say this is, if this is a right, if this is the wedge, then this needs to be the dash. Okay, because it has to go in the opposite. This p orbital over here has to go in the opposite direction for how we want this bridgehead to go, which makes this one into a wedge. Okay? And so what we're going to do is we're going to make this really big, right? So that attacks here, that's going to go there, that's going to go there. And so that's there. So this blue CH2, right, it's going to go here, CH2, like that. Now, in this case, we need this to go down, so on a dash, right, because our bridgehead is on a wedge. So CH3, which means this one also has to be on a dash because it's on the same side of the dienophile. So this also needs to be on a CH3. That means this ethyl group, so CH2, CH3, this side has to be on a wedge, like this. So that's our product. Okay. So if you want to have this be your hydrogen, it would be there. Now for UV spectroscopy, okay, it works the exact same way as every other form of spectroscopy. Okay, but here we're going to be using both the visible as well as into the ultraviolet. Okay, so we're going to be going from about 700 nanometers to roughly 200 nanometers. We're going to be in this range here. Okay. Now again, don't forget that when we're talking about wavelength, we're talking peak to peak. Okay, so frequency is how many peaks per second. So it's, if you're talking about hertz, you know, something that's at 200 hertz, that means it's a peak is coming by you 200 times per second. So hertz is a second. So if you're talking about megahertz, right, that means, you know, if it's at 200 megahertz, we're talking about 200 million, you know, things per second. So in this case, it's peaks per second. So, okay. Again, the shorter the wavelength, the higher the energy photon, right? So as this gets shorter, right, energy goes up, right? Because you're dividing by a smaller and smaller number. So just like every other spectroscopy, you're going to shine. We know what light we're sending into it. How does our molecule interact with that light? And it turns out UV spectroscopy is really good at looking at conjugated systems, which is why it's in this chapter. Okay, and again, we're looking at the absorbance, so how much is absorbed per wavelength here, and we're looking at this peak. And so for here, it's going up. It's the opposite of IR, which was transmittance. So here is how well does it absorb. Okay, and so we look at the wavelength at which there's a maximum. And so for here, if you look at this molecule, it absorbs right there. It turns out that, so the way this works is that because you're using a conjugated system, what you're doing is you're using the pi system. What you have to do is you have to align the energy of the photon with this gap. Okay, and it's what's called the HOMO-LUMO gap. Okay, it's the hot, so you have an electron here, you have no electron here, so this is the highest energy occupied molecular orbital, and you send it up to the highest unoccupied molecular orbital. So it's what's called a pi, and so you come in here, so HOMO-LUMO, basically what's happening is you're sending it from the pi, the p orbital, up to the p star. Okay? And so this is the bonding orbital. This is an anti-bonding orbital, which is a higher energy. And so when you absorb that, right, when it absorbs that energy, we can measure that. Okay, and it's what's called and the gap is what's called the HOMO-LUMO gap. Okay. Now you can measure. One of the nice things about this is you can use what's called Beer's law, which is you can tell absorbance by looking from absorbance. You can get concentration, if you know the path length and what's called the molar absorptivity or the extinction coefficient. Okay, and this is every molecule is going to have a slightly different absorption. So you either look it up in the big book of extinction coefficients or you Google it. Okay, somebody had to measure what this is for your molecule. Okay, so by that, but we have to take into account path length, because if we send it through twice as much material, we're going to absorb twice as much light. Okay, if we send it through half, we're going to, half of what a shorter length instead, it's just not going to be able to the light won't be interacting with the molecule as much. Okay, so we have to take that into account. Okay, so the absorbance that you measure is equal to this constant for the molecule, and it's different for every molecule. The path length, and usually this is 1 centimeter, which is nice because it makes the math easy, and then the concentration of the sample in molar. Okay, and so these work pretty well. So if you have concentrations, so calculate the molar absorptivity. If it's, so you've got equals extinction coefficient. I usually do a cursive L, and then times concentration. So I know it's not a 1. Okay, and so A is equal to 0.78. Okay, the concentration is this in molar. So concentration is 0.6 times 10 to the minus 5 molar, and then the path length is 1 centimeter. And if it doesn't say, it's almost always going to be 1 centimeter. And so for here, what we're going to do is the molar. So if you know what the concentration is, right, you weigh it out, you put in the exact amount of water, with the water is, you can get a concentration. So what we're doing is, usually 3 of the 4, and so the you can find the 4th one. And so for here it would be 0.78. The extinction coefficient we don't know, 1 centimeter, and here it's the concentration is 0.6 times 10 to the minus 5 molar. And so when you do this, right, you're going to divide both sides by 0.6 times 10 to the minus 5. Right. And so you end up with this. Here's the molar absorptivity. Pretty simple. You're usually given, you've got 4 variables, you're usually given 3 of these, and you just have to plug it in. Not too bad. Now, one of the things that can happen with this is that the trend is, the longer the conjugation, the longer of wavelength of light that it absorbs. And so if you have something like ethylene, okay, just one, as you add in additional conjugation, right, notice how the wavelength goes up. And so coming here, you've got 454, right, for beta carotene, the orange and carrots, right? So look at all this conjugation here. If you look at lycopene, which is red, in the right, in tomatoes, it's right here. Here's the conjugation. So for the orange, it's here, right? But as you continue to add conjugation to the molecule, you will increase the wavelength at which it absorbs. Okay. Now this can be important for things like dyes. Okay, so you can look at, a lot of these dyes, you have fabric dyes, okay, are going to have these really extensive conjugation networks here. Okay, particularly if you're going to be adding nitrogens and oxygens and things like that. Okay, that's it. Good luck.